All right, here we are again, and we are going to have another look at sound intensity, but this time we're going to look at it from the human perspective. What I mean by that is we're going to try to get some kind of appreciation for how intense the sound actually is. You'll recall that we've learned so far that the intensity of sound, I, is measured in a unit called watts per square meter. And I'll remind you that intensity is equal to power divided by area, remember? And so that would be watts per square meter. But the problem is nobody really knows what a watt per square meter is, unless you have a mental picture. Remember the Newton? When we introduced the Newton, we said that we needed a mental image, and we said it's about the weight of an apple. So we kind of know that 10 newtons isn't that much. But if I were to write 10 watts per square meter, you wouldn't know if that was a tiny, quiet sound, or if it was a very extremely loud sound. You don't really have a benchmark. So we're going to hopefully get a benchmark out of all this that we're going to do. What we do for humans is we use a different kind of unit, and we write the intensity a different way. Intensity. Instead of using an I, because we're changing the unit, we use a little beta, which is Greek B, capital B, beta. It's still pressure per unit area, but the unit is different. It's going to be measured in a unit called the decibel, which is a little d and a capital B for short, decibel. And you remember that in the metric system you have, say, the meter, and then you can have a decimeter, and a centimeter, and a millimeter, and so on. Well, this decimeter is 1/10 of a meter, right? Well, the same is here. It's a decibel. So the actual unit is really the bell. It's named after Alexander Graham Bell, I think, who invented the telephone and did a lot of work with sound. When he invented the phone, by the way, he was actually trying to find a device to help deaf people hear better, or people hearing impaired. And incidentally came up with the telephone out of all that, which is kind of neat. So the bell is the unit, but it's a decibel because we use tenths of it, tenths of the bell. And that's just so we get convenient numbers. So that's what we're after. So first, let's talk about the logarithmic scale that we're going to use. First, we'll draw a regular scale that you're accustomed to. A scale that starts at 1 and goes up by ones, and so on. This is called a linear scale because each time you move a jump on the scale, you add 1 to where you were before. 1 plus 1 is 2, 2 plus 1 is 3, and so on. But this kind of a scale gets pretty cumbersome if you have to go a long way. If you have a large range of data, and you have to go from 1 up to numbers of 1,000,000 or 1,000,000,000 or 1,000,000,000, the scale becomes incredibly long and cumbersome to use. So for large ranges of data, we use a different kind of scale called the logarithmic scale. Logarithmic scale. And you'll learn more about logarithms in your grade 12 math class. But for now, we'll just kind of get the idea. And you've already seen a logarithmic scale in grade 10 in your chemistry class when you did the pH scale. It also has numbers 1, 2, 3, but the numbers stand for something else. So on. Here, the numbers stand for an exponent. So this would be 10 to the power of 1, 10 to the power of 2, 10 to the power of 3, and so on. But we don't write the 10, we just write the little number, that's the exponent, on the scale. Which means that when you go from 1 to 2, it's not 1 plus 1, it's 10 to the 1 and then 10 to the 2. Well, that's 10 and then 100, right? this would be 10, this would be 100, this would be 1,000. So what's happening is you're multiplying by 10 on each step of the scale, times 10 times 10. And that means that you're going to climb up through the data faster and get to larger numbers faster. On this scale, we can get to 1,000,000 and only have to go up to the number 6. Right? So we can use a much smaller scale. That's what a logarithmic scale basically means. What we're going to do is we're going to use a logarithmic scale to represent sounds. So, from a human perspective, sounds can come in any intensity, but the ones that matter to us are the ones we can hear. So for us, there's going to be a quietest sound. Quietest sound that humans can hear. Let's put humans here. Because obviously if you're not a human, if you're an elephant, you can probably hear sounds that are quieter than this, but humans, this will be their quietest sound. And then the sounds will get louder and louder and louder until you get to the loudest sound that a human can tolerate. Because remember, loudness or intensity is related to the amplitude of the vibration, right? So quiet sounds have low amplitudes and loud sounds have large amplitudes. And these amplitudes are the degree of vibrating. So a loud sound with a big amplitude will cause a large vibration in your eardrum and in tiny bones inside. And if it's too large, it'll break them and your ear will be damaged. So the loudest sound that humans can tolerate without starting to damage their ear is what we call the loudest sound for humans. Sure, you could listen to a louder sound than that, but only once, because then you'd be deaf, right? And it turns out that the quietest sound that humans can hear is 10 to the negative 12 watts per square meter. That kind of a vibration would be the quietest. So the quietest whisper. Picture a cat's paw walking across, how quiet cats are. Imagine their footfalls on a hardwood floor. Tiny, quiet vibrations that you can barely discern would be about 10 to the 12 watts per square meter. And the loudest sound, believe it or not, is 1. 1 watt per square meter is about all a human can tolerate without feeling pain in their ears and possibly doing damage. So that's what we consider to be the upper limit. So if we were to make a scale, you can see how our scale would have to be quite large. We'd have to go from the quietest sound, which is 10 to the negative 12, and we'd have to go all the way up to 1. Well, that's a difference of 1 trillion. So that's a lot of little marks. So we use a logarithmic scale. And we make a scale with 12 ticks in it. So we would go from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And to get from this value to this value, we use exponents. Now, normally, if we use exponents, you'd be going backwards, right? We would say 1, and then 10, this would be 0.1. The next one would be 0.001, going down by tens each time, because 1 is at the end of our scale instead of at the start, which is weird. That just means you'd be getting 10 times smaller each time. And so this would be the power, this would then be to the negative 2, to the negative 3, to the negative 4. These were the powers of 10, right? And negative 5. Well, the negative sign is kind of complicated. So we want to get rid of the negative sign, and we want the scale to go the other way. So what we do is we flip the logarithmic numbers upside down. So we put the 1 down here, and then the 2 and the 3 and the 4 are going this way. But it's really the same amount, it's the same thing, it's just kind of like if you cut off these blue numbers and flip them the other way. And then to get numbers that are convenient, we multiply them by 10. So our decibels tend to go 10, 20, 30, 40, 50, 60, 70, 80. So they take the logarithmic scale and they actually flip it. And then they mess with it a bit. But it's still a logarithmic scale, it's just a little more complicated. All you have to remember is that each time this happens, it goes up by 10. Okay, so let's get our heads around all that by making a nice convenient chart, right? So we'll draw our chart. here. And we'll put some numbers in the chart. We'll put the intensity I, which will be measured in watts per square meter. And then beside that, we'll put the intensity beta, which is also the intensity, but it's going to be measured in what we call the decibel, our new little unit. Okay? So they mean the same thing, they're just a different unit. It's like measuring distance in miles or kilometers, or measuring it in furlongs or leagues or weird units. If you were writing a novel that was set back in 1812, you might use the word leagues or furlongs like they used to. But if you're writing the novel for today, you would use meters or miles or something we understand. And then over here we'll put an example to give us some idea of how loud that actually is. We'll start with the quietest sound that humans can hear, which is 10 to the negative 12 watts per square meter. And we call that basically, since remember the decibel system is based on human hearings, or the human range, this would be the bottom of our range, or the lowest sound, so that would be basically 0 decibels. And this is also called the threshold of human hearing. The threshold of human hearing. Okay. I won't write that in, but you might want to scratch that down on the side. Threshold is a word that means the beginning. When you have a doorway, a little piece of wood at the bottom of the door is called the threshold. When you get married, you carry your bride over the threshold, right? It's like going into the house or the beginning. So the threshold is like the lowest limit. How quiet would that be? Well, it's hard to define. It would be the lowest audible sound. It would be the smallest amplitude of vibration that humans could possibly hear. In other words, at this point, anything below this you wouldn't hear. So there's no real example for that, it's just, that's the limit. Then we move up 10 times louder than that. So 10 to the negative 11. 10 to the negative 11 would be 10 decibels. And to give you an example of how loud this is, you can think about when you have a nice summer day and there's just a little breeze and the leaves on the trees just begin to rustle a little bit. That little rustling of leaves sound, that would be about 10 decibels. So it's not very much. Rustling leaves. Not, tornado, hurricane winds, but just the ever so smallest breeze. So 10 decibels is very quiet. But that's 10 times louder than the smallest sound you could hear. Right? So it's still a big difference. Then, maybe if I draw lines in between, because this is going to get to be a little bit confusing. That'll help. The next level would be 10 times more, so 10 to the negative 10 watts per square meter, which would be considered 20 decibels. Okay? So 10 to the negative 10, oops, it would be 20, sorry, 20 decibels. So this is 10 times louder than rustling leaves, 20 decibels. An example that we could use for this would be someone standing a meter away from you and just whispering to you. A whisper at 1 meter. Be very quiet. 20 decibels. Then we go 10 times louder, 10 to the negative 9, which would be 30 decibels. Well, the example that we have for 30 decibels is a whisper, but only a ruler's width away. So they say, if that person got closer to you, remember how we said the closer you are, the louder sounds get. A whisper at 30 centimeters, 1 ruler away from your head. And that would be about 10 times louder than whispering a meter away from you. Okay, let's go a little bit more here. We're going to need to extend this chart quite a bit. 10 times louder than that is 10 to the negative 8, which would be 40 decibels. And believe it or not, 40 decibels is about the sound of this room right now. quiet room, away from traffic, or where there's no disturbing noises. Right now you think this room is almost silent, but you can hear the fan of this little thing humming. There's the odd little noise from the hall, right? So if I'm not talking, there are still some noises that you're hearing. So the level of sound in here is actually 40 decibels. The background hum of things around you, basically. Okay, let's go next one. And I'm going to make my lines go a little bit bigger here. 10 times louder than that would be 10 to the negative 7 watts per square meter, which would be 50 decibels. And the book here that I have says that's about the sound of a car engine 30 meters away. I suppose an idling car engine at 30 meters. 30 meters is a long way, right? It's probably close to the length of this school. So you stand at one end of the school and you see a car, its engine is running that far away. That's how loud that would seem. And these are just estimates, right, to give you an idea. The next one would be 10 times louder than that. 10 to the negative 6. 60 decibels. And that's normal conversation, so not whispering anymore. When you talk to somebody without screaming or yelling at about 1 meter away, that's about 60 decibels of noise level intensity. 10 times louder than that, 10 to the negative 5 watts per square meter. 70 now. 70 decibels. Now we're starting to get kind of loud. This would be like standing on a busy street corner and listening to all the cars going by and all the noise, a busy intersection. Or the book says could also be the sound of a train, but the train would be about 30 meters away. So I don't like the ones that have a distance because it's hard. How far is that? But you can all picture standing on the corner of Second Line and Great Northern Road over here, and just the amount of noise around you would probably be somewhere around 70 decibels. Okay, 10 times louder than that is going to be 10 to the negative 4, which would be 80 decibels. This is the sound of a subway. If you've ever been down to Toronto and you hear the noise as the subway goes by, or another option that they give, which I like, is close to Niagara Falls. If you've ever been to Niagara Falls, there's a huge roar as you're standing up on the observation deck there, not far from the water rushing over the side. And whenever I go there, I can't help but imagine what it would be like to be caught in that water, knowing that very soon I'm going to go over the falls, and how you panic and how scary that would be. But luckily that hasn't happened yet. That's how loud that would be. 80 decibels, quite loud. And just incidentally, if you remember, each step is times 10. So if we were to go back from Niagara Falls and go back 10, 100, 1,000, 10,000, 100,000, a million, 10 million times louder than rustling leaves. Niagara Falls, 10 million times louder than rustling leaves. So it's huge. Your ear is incredibly sensitive, isn't it, to be able to hear the differences along such a great scale, which is why we have to protect it and why loud sounds can damage it. It's incredibly sensitive. It's a miracle of Mother Nature's engineering. 10 to the negative 3 would be 10 times louder than that. We're up to 90 decibels. Getting pretty loud now. You know what a jackhammer is, the pneumatic drill, that thing they break up pavement with. So they use a jackhammer or a loud lawnmower. Maybe a lawnmower is better because we all know what that is. That's a pretty loud machine, right? A lot of us don't even bother to wear ear protection when we cut our grass, and we're exposed to this loud lawnmower for a great period of time. There's a high risk there for doing some damage to those sensitive hairs inside your inner ear. 10 to the negative 2, 100 decibels. Here they use the sound of a motorcycle. A motorcycle. And again, a motorcycle can be idling fairly quietly, or it can be revved up very loud. So I'm assuming they mean, a big Harley as it takes off at the traffic light and makes a whole lot of noise. Or they also use the example of a chainsaw, which is pretty annoying. Believe it or not, there are some people who snore, and the decibel level of their snoring has been measured to be somewhere between 80 and 100 decibels. So imagine trying to sleep beside somebody who snores as loud as a chainsaw. That's pretty crazy. Okay, we're almost done. We have a couple more. Because once we get to 1 watt per square meter, remember, that's going to start to be painful, so we don't go any further than that. But 10 to the negative 1, and that's 110 decibels, sorry. And we're talking about a sound here that's a loud rock concert near the stage. Obviously, at a concert, if you're farther back, it's not quite as loud, but near the stage, some people like to get right up front and try and grab somebody, or maybe have some of their sweat fall on them or something, and they're like, oh my god, I'll never shower again. It's great. But I think that's kind of gross, and diseases are spread that way. But if you get right up close, you're right up close to the speakers, and the sound at that level would be incredibly loud. There was a famous rock band called The Who. You probably have heard of The Who. And back in the 70s, they were renowned for giving the loudest concerts ever. They had their concerts were so loud, and they would play this loud music. And Pete Townsend, who is a guitar player for The Who, has so much hearing loss that he has difficulty hearing children's voices. Even his own kids, when they talk to him, he's really got to struggle to hear them, because kids' voices are higher pitched, and you can't hear them because all those years of playing with loud music has damaged his ears to the point where he can't even hear kids talking. There are days when I think that might actually be a good thing, but I think in general it's probably pretty bad. Okay, so now we're at 10 to the 10 to the 1, or 10 to the 0 actually, right? 10 to the 0 would be the next one in the scale, but anything to an exponent of 0 equals 1. So we're at 1 watt per square meter, which is 120 decibels. This we call the threshold of pain. So the lowest number was the threshold of hearing. This means that after this, it's going to start to hurt. And if it's starting to hurt, then that obviously means that there's potential for damage. So this is what we consider to be sort of the upper limit of intensity that humans can tolerate. Incidentally, there have been all kinds of research into using loud sounds as a weapon, right? An extremely loud vibration would cause so much pain in your ear that it could disable you. And so the military has experimented with loud sounds that cause pain. But ideally, we don't want to get anywhere near this. Just to give you a comparison, the textbook that I got this chart out of actually has another number. It just kind of goes dot, 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 dot. And it goes up to, jumps to 10 to the 6. So imagine if you went, the next number would be 10 to the 1, 10 to the 2, 10 to the 3, and so on. If you went up to 10 to the 6, that would be at around 180 decibels. And that's the amount of sound that you would hear at a rocket launch pad. So if you were to go stand beside the space shuttle when it was taking off, and not have ear protection, well, first of all, if you stand that close, you're going to get burned up in all that, all the fumes and flame coming out of the engine. But if you could get really close to a rocket like this, as it took off, you would probably hear one very loud boom. You'd experience a little bit of pain, and then you'd need a lot of Kleenex to sop up the blood that was oozing out of your ears, because your eardrums would be blown completely out of your head. So we just can't tolerate those kinds of things. Many people work in conditions where the decibel level is anywhere in this area. If you work in a steel plant, or if you work in a place where there's loud machinery can be, 80, 90, 100 decibels. And so this is why, of course, most people who work in situations like this have to wear ear protection, because if you're exposed to these, if you're exposed to, the lower end of this for 7 or 8 hours, it can actually cause the same amount of damage as being exposed to a higher level for only a few minutes. So ear protection is necessary even when it doesn't seem that loud, if it's going to be for a long time. That's what people don't seem to understand. So that's the decibel system. Now all we have to do now is learn how to convert one into the other. A little bit of math. And so it's not that hard. I'll give you a couple of examples. There's a simple formula that we can use. And then I'm going to have to show you a little bit about how it works. The intensity level in decibels, from a human perspective, is equal to, and this is where we use the logarithm thing, it's equal to 10 times the log of I2 over I1. Remember, I is the intensity in watts per square meter, and beta is the intensity in decibels. And there are two ways to use this equation. First of all, let's explain how we use the log. It's quite simple. There's a button on your calculator that says log, and you press it, and that'll do all the work for you. So you really don't need to get into too much heavy math. But I will help you in a minute with something else. So, how would we, first of all, use this to convert? So this can be used as a conversion. So to use it as a conversion, I'll show you how it would be. Let's have a question that says, a sound has an intensity of 6.4 times 10 to the negative 7 watts per square meter. What is the intensity in decibels? How do we figure out how many decibels that is? Well, we use the formula. The formula says that the intensity in decibels is equal to 10 times the log. Now, what does this I2 and I1 mean? When we use this formula to convert, the bottom number, I1, is always the threshold of hearing. Because what we're doing when we use decibels is we're comparing the loudness of a sound to the quietest sound we can hear. That's what decibels do. So the bottom number here is always the threshold of hearing, which means it's always 10 to the negative 12 watts per square meter. So that number doesn't ever change when we're using this for a conversion. And then the other number that you want to convert, which is this one in the question, is the one that goes on top. Remember that fractions are also comparisons, right? So we're comparing this intensity on top, the 6.4 times 10 to the negative 7. We're comparing it to the lowest sound we can possibly hear, and that's going to tell us how many decibels it is. So we write P equals 10 log, and on top of the fraction we write our 6.4 times 10 to the negative 7 watts per square meter, and we compare that to 10 to the negative 12 watts per square meter. I won't put the units in because, they're going to cancel, aren't they? They're going to cancel anyway. Okay. So the first thing you do is you take out your calculator, and if somebody could do this for me while we do it, that'd be great. And you put 6.4 times 10 to the negative 7, and you divide that by 10 to the negative 12. And if you do, what do you get? Somebody divide those two numbers for me. If 2 or 3 people do it, we can double check that we get the right answer. Did you get it there, Nick?
No.
Anyone? I know it's first day after the long weekend. It's a lot to ask to punch those numbers in. Your fingers must be sore from, I don't know, gripping the bars at the fair all weekend, holding on to the rides. Who's got that number for me? Okay, so you got 0.4 times 10. 6.4. Okay. You grab that door for him. 6.4 times 10 to the negative 19. Okay. Well, that kind of makes sense, eh? Because if you look at the exponents, what's the difference if you're dividing? How many times do I go into that, right? So 6.4. Okay, now all you have to do is press the little button. Did you get a different answer, Below? Yeah, okay, that might be better. Let's double check. I think that one sounds more reasonable. 640,000. Okay. All right, so that's about where we are on the scale. Now press your log button. You should find a button that says log. And on some calculators, as soon as you press it, it'll give you the answer. On other calculators, it'll write log answer, and you have to press equals to get the answer. But what do you get when you multiply that, or when you press the log button after that number? So you'll have b equals 10 times what? I think it's going to be 6.4, because you can tell by the number. But I want to make sure you can do it on your calculator. What'd you get? 4.8? 5.8? We all have to get the same number. So you either have to press log and then 640,000, or you have to press 640,000 and press your log button. Depends on your calculator. 5.8? That sounds reasonable, I guess. 5.8. Anybody else get that? And then you multiply it by 10, and here we are, 58 decibels. And we can put the decibels in now. Don't confuse the B that's a Greek-looking B with the capital English B in the decibels. So that's 58 decibels. So that's a sound, right? Although it doesn't seem like much, that's pretty loud. If you go back to our chart, 58 decibels is right about here, and that's the sound of the conversation. So reasonably loud. Okay. Where this gets difficult is if you have to do the opposite. If you have to figure out an intensity. So let's do a second example, and this should be the end of it. Actually, there's two more examples. We lost one. The second example would be this. Example 2. What is the intensity in watts per square meter of a sound at 46 decibels? Now, if I had said 40 decibels, you could go back to the chart and just look it up, right? You could go right back to 40 and say, oh, well, I have that on my chart. If it's an even number, if it's 10, 20, 30, 40, 50, 60, 70, 80, excuse me, you can go back to the chart and just cheat. You can, oh, it's 10 to the negative 3. We do know, though, that our answer should be, if I said, what was it, 46 I said? Well, 46 is somewhere in here. So we need to be somewhere between these two numbers when we get our final answer, right? And we can double check. If you get an answer of 209, you know you did some math wrong. You know that 46 is between 40 and 50, so the answer in watts per square meter must fall between these two numbers. But we can't read it directly off the chart, unfortunately, so we're going to have to do the calculation. So we'll go back down and see how this works. This is going to require a little bit of fancy calculator work. If we write the formula down, it's the same formula, 10 log I2 over I1. And remember that I1 is always 10 to the negative 12 watts per square meter, the threshold of human hearing, when we use the formula this way. So let's fill in what we've got. This time they're giving us a 46 for the beta, 10 log, and now they want us to figure out this I2, 10 to the negative 12 goes here. So we have to figure out what kind of algebra we will need to make this work. Well, the first thing we can do is divide both sides by 10, right? And we get 4.6 equals the log of I2 divided by 10 to the negative 12. But now what do? If we haven't learned about logarithms, this becomes difficult. But on your calculator, there's a cool button that's kind of the opposite of logarithm. It's like the unlog button. And look for one that says 10 to the x. It's probably near the log button, or it might be the shift or inverse of the log button. So you can press shift log. So now what you're going to do is you're going to unlog both sides. This is the opposite of log. I guess I could try to explain it to you, but that'll just complicate things for now. So let's just learn to use the button, and then when you get to grade 12 math, you'll be like, oh, now I see why that button works. So what you want to do is you want to take 4.6 and press your 10 to the x button. And what do you get? What you're saying is, please tell me what 10 to the 4.6 would equal, right? And what is that, 10 to the 4.6? It's got to be bigger than 10,000, but not bigger than 100,000. 9836? No. 39,810? Yeah, somewhere between 10,000 and 100,000. That's perfect. Now, when you unlog the other side, if you 10 to the x this side, all that does is remove the log. So at that point, you're just left with what was left in the brackets. Because it's kind of like when you do the inverse sine, right? It's the same idea. This function undoes this log function. So that's how you, I should have wrote this over here so you remember to use it right here on the 4.6 to get to there. Well, now you just multiply both sides by 10 to the negative 12, and so you would get what? I'll do it down below so it doesn't get confusing. What's this number times 10 to the negative 12? Well, you're just going to basically move the decimal point 12 places, right? So you're going to move it 3, 4, 5, and then another 7. So I'm thinking, is it 3.4 times 3.9 times 10 to the negative 8-ish? Yeah, 3.981 times 10 to the negative 8. And that would be watts per square meter now, and that's I2. And if we go back up, 3.9 times 10 to the negative 8, that should be right in that little ballpark that we had said. If we go back to the chart, we'll double check. Where the chart is, here it comes. 3.9 times 10 to the negative 8 is actually between these numbers. So that makes sense. So you can always double check with the chart. So if you you don't have to memorize the examples, but if you kind of memorize the numbers of the chart, which are really easy to memorize, right? Then you can actually compare it and make sure that your answers match up. Okay, now there's one other way to use this formula. So we've used it as a conversion. We've changed watts per square meter into decibels in the first example. And now we've seen that by using that fancy button on the calculator, we can also change decibels back into watts per square meter. But there's another way to use this formula as a comparison, because it is a comparison formula. So the first way was the conversion way. This way is the comparison way. So a comparison doesn't give you an actual number, it just gives you a comparison. Watch. You can compare two sounds. That, up a little bit more. Okay. Here's an example of how you would use the formula to compare. How much louder in decibels is 2.4 times 10 to the negative 3 watts per square meter sound compared to a 1.7 times 10 to the negative 6 watt per square meter sound. So we want to just know, we don't really care exactly what the number is, we just want to know how much louder it is. So we can use this little formula to compare and get an answer. So watch. This time, the I1 on the bottom will not be the threshold of hearing. What will happen is on the bottom, we'll put the quiet sound, or the quieter sound, and on the top we'll put the louder sound. So obviously this first sound is a bigger number, right? It's more watts per square meter, so it will be the louder sound. So we'll put that on the top, and then we can just simply crunch it out. So we would get this. It's 10 log, and then, of course I can't remember my numbers that I just wrote, so 2.4 times 10 to the negative 3 compared to this little tiny sound, 1.7 times 10 to the negative 6. So if somebody could divide those two numbers for me and tell me what that actually works out to in the brackets, we could jump to the next step. What's in the brackets? I think Karen's going to get it. Somebody got something? Don't be shy. 1,412. Did anybody else get something close to that? Okay. Now what happens if you press the log of that button? Press the log button to get the log of that. The log is going to be something like about 3 point something, eh? 2.15. And then if you multiply that by, so you get 31.5 decibels. Now that doesn't mean that's the actual level of the sound. What that means is that the first sound, sound A, is 31.5 decibels louder than sound B. Right? That's what that means. So it's kind of like, you know, if I say, well, what's the difference between the money in my pocket and the money in your pocket? And you have $100 and I have 80. Well, the difference is 20. That doesn't mean we have 20 bucks. It just means, and the difference could be, I could have had 150 and you had 130. That's still a difference of 20. So this is a comparison that tells you how much one is louder than the other, but it doesn't give you an actual level. So it's not a conversion. And to do that, the big difference is you don't use the threshold of hearing on the bottom. You're just comparing two regular sounds as opposed to comparing to the human limit. Okay? Now, of course, we could also mention for fun that other animals have different ears and different structures in their ears and different designs, so they perhaps could hear sounds that are quieter than ours. We all know that dogs can hear the quietest sounds that we don't even know exist. They start barking and I'm thinking, what are you barking at? And there could be animals that could tolerate louder sounds than we can, depending on the structures of their ears. But for humans, this is how it is, and this is how we perceive the world. All right, so that's basically the end of that.